So in our problem that we're going to try and solve this time, we have an infinite slab of charge of thickness 2a. So from here to here is 2 times a. It's centered in the xy plane, so the xy plane goes down through the center. That puts our z-axis coming up from there. Centered in the xy plane, the charge density is uniform. That has a symbol of rho. Find the electric field strengths inside and outside the slab or block of charge. This is an edge view. If you were trying a 3D view, and my 3D drawing is not super, so bear with me. So edge view. Would have the block like this. So it goes through the xy plane, and our z coordinate system goes up through the middle. So z comes out the center. Z-axis. Okay, so that's a picture of what we have. We have positive charge uniformly distributed throughout the entire block of charge. If we're going to try and find the electric field, then we're going to use Gauss's law. Gauss's law states that the net electric flux through any closed surface is the integral of E dot dA, which is equal to the net charge enclosed by that Gaussian surface divided by the constant epsilon naught. So we know we need to have a Gaussian surface, so we have to choose what is a good Gaussian surface. And we'll remember that we're trying to find the electric field inside and outside. So first off, let's pick a Gaussian surface that the symmetry of it will be the same no matter we're talking about inside or outside. So let me draw a picture for what I'm talking about. And in general, to take advantage of the symmetry, you pick a Gaussian surface that looks like your object. So for my object, and I'm not going to work with the 3D view because it's just too hard to draw, I'm going to go with the two-dimensional view. So if I want to find the electric field inside, and that would be where z is less than a, then the Gaussian surface I would draw would be a box that's entirely within my surface. And in this case, this box encloses part of the charge within the surface. So I know that my Q enclosed will be less than my total amount of charge. If I want to find my electric field outside, that's for Z greater than A. I'll draw my box again. This time my Gaussian surface is still going to be a box, but it's going to extend outside of my plane, outside of my block of charge. So let's define what my Gaussian surface is. My Gaussian surface is a box. It's got cross-sectional area A. So the area of this top face right here, in 3D it would kind of look like this going down through the plane. And the thickness will be from here to here. So that's the thickness. So from minus Z to plus Z. And what else? Our Gaussian surface will be centered on Z equals 0. So symmetrical about the center. Okay, so there's lots of details about our Gaussian surface. It's the trickiest part, so it's kind of good to get the details written down. So the next thing we're going to do is let's deal with this part of Gauss's law, the integral of E dot dA. Our symmetry is the same for both, so our result for the integral of E dot dA should be the same for both. Our Q enclosed is the part that's going to change. Okay, so let's do that part next. The integral of E dot dA is going to have three contributions. So we've got E dot dA, the flux through the top surface, E dot dA, flux through the bottom surface, and then we've got our flux through the side surfaces. Let's get a picture of our electric field vectors on there. So our electric fields, and remember this plane is infinite in the xy direction, tells us that our electric field vectors point straight out. So there's our electric field. Now let's get to doing E dot dA for each of the faces of our box. For the top face of our box, the dA is a little area element on the top face of the box. There's my dA. I see here that my E points straight up, my dA points straight up. Those two vectors are parallel. So the integral of E dot dA is the integral of E times dA times cosine 0. E is a constant value because we have this planar symmetry, so the E comes outside. Outside the integral of dA. Cosine of 0 is just 1. The integral of dA is A. Okay, let's do the bottom next. On the bottom, the area element sticks straight out. So the bottom is just like the top. Okay, last we have the sides. On the sides, our area vector sticks straight out. So on the two sides that we can see, they're perpendicular. On the front, it comes out this way. That's also perpendicular. So E dot dA is equal to E times dA times cosine 90 degrees equals 0. Okay, so what we've just found out is that our net electric flux is EA plus 0. Oh, and just before we move on, we'll show that it's the same on the outside. The outside, the dA on the top face is up, same. dA on the bottom face is down, same, and on the sides is perpendicular. So our result is true for both inside and outside. Okay, so my net electric flux is EA plus 0 equals 2 times E times A. There is half of our Gauss's law done, the net electric flux. Next we have to deal with Q enclosed. Here's where our two cases are going to be different. Here, our Gaussian surface only encloses a piece of the block, so we'll only have a piece of the charge. Here it encloses all of the block, so we'll have all of the charge. These guys are different. We're going to have to calculate those separately. So let's do inside first. So inside my block, and I think I might even just draw it again here. So there's my block, there's my uniform charge distribution. There's my Gaussian surface, and there's my Z equals 0 line. Okay, so inside, we're trying to find Q enclosed so that we can apply our Gauss's law. Q enclosed equals the density times the volume. The volume of our Gaussian surface, well, it's got a thickness of this much plus this much, and it's got a cross-sectional area of A. So I've got density times volume. Volume is the thickness times the area. Okay, I am being a little bit careful here. I know that my charge is positive. Oh, my thickness is 2Z, sorry. I know that my charge is positive, but my Z, since this is Z equals 0, Z can be plus or minus. If my charge is positive, I need my Z to be positive, so I'm going to take the absolute value of my Z here. Okay, hopefully that's clear. So it's density times volume. Volume is area times thickness. 0 goes down the middle, so the height above 0 is z, the height below 0 goes to negative z. My total thickness is 2 times the absolute value of z. My thickness has to be positive. Okay, so there's the amount of charge inside. Now I'm going to apply Gauss's law. Net electric flux is the integral of E dot dA equals my charge enclosed, which is 2 times rho times A times the magnitude of Z. Absolute values here because I need my charge to be positive, divided by epsilon naught. So I know from my previous result E dot dA is 2 times E times A equals 2 times rho times A Z over epsilon naught. We have some stuff cancels. We have a 2 on either side. We have an A on either side. We're left with that the electric field is the density times Z over epsilon naught. Electric field is a vector, and the direction of my electric field vectors is outwards from the center. Okay, so this is my result when I'm inside the block. So this is true between minus A and plus A. Okay, let's do outside next. So I'll redraw my picture again. There's my axis, here's my block. There's my charges, and here's my Gaussian surface. Let's be really careful with notation. The distance from the center to the top of my Gaussian surface, that's Z. The distance from my center to the top of my block of charge, that's A. We have to be careful here because when we find the Q enclosed, there's only charge on the block. So once we're outside, Q enclosed equals rho times V. This V refers to the volume of the charged object. Inside the Gaussian surface. I'll just do GS for Gaussian surface. So this white space here doesn't count. There's nothing charged there. It's only this stuff that we need to find the charge on. V is the volume, so that's going to be the cross-sectional area of my Gaussian surface times the thickness. The thickness is going to be 2 times A. A itself is a positive number, so I don't need to put in my absolute value signs here. There's my Q enclosed. I'll write down my Gauss's law next. My net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. I already found out that E dot dA is 2E A equals my Q enclosed, which is 2 times rho times area times thickness divided by epsilon naught. 2's cancel, A's cancel, E equals rho A over epsilon naught. Electric field is a vector, of course, and the direction is outwards from center. Or I suppose from here would be outwards from the block. And then last, we weren't asked to, but we might wish to make a graph of this electric field. If we were going to plot the electric field, we would plot it as a function of z, so it's a function of our distance from the center. So there's z, there's the electric field. Inside, the electric field is proportional to the distance, so it's going to be linear. And outside, it's going to be constant, so it would go horizontal. And this value here would be rho times A over epsilon naught. So there's a plot of the electric field as a function of distance from the center.